Thank you very much. Thank you, Diane. Well, welcome everyone, and thank you very much for coming along tonight or this afternoon, wherever it was. Oh, we've gone beyond the slide. Just to introduce myself, my name's John Kerr. I'm the Training and Networks Manager for Zero Carbon Harrogate. We're a charity based in, no surprises, Harrogate, and what we do is we're trying to achieve zero carbon through various initiatives. We started nearly 3 years ago now with a retrofit program, essentially looking at trying to encourage retrofit across the whole of what was the Harrogate district at the time, doing both education of homeowners, but also looking at, with funding from Ofgem, looking at skilling up the existing construction industry in and around Harrogate and the wider area. That's developed on, and we were invited to bid for a LEAD program with the Department of Energy Security Net Zero, which LEAD stands for Local Energy Advice Demonstrator, and essentially a bigger scope than what I've just described. So still looking at educating homeowners, but right across North Yorkshire, so the whole of the county, and a much bigger budget in terms of training and upskilling the existing construction industry, along with looking at developing, I would call retrofit professional as well. And I'll just go into that in a few seconds. So the homeowner side of it, which the unique part of LEAD, is that we have a fund of money to look at providing whole house retrofit plans free of charge for target areas around North Yorkshire. So Harrogate was one of those areas, Selby's another, Hutton Rugby Stokesay, which is in the northeast of North Yorkshire, Skipton and Pickering. So I think that's the main areas. And what we're looking to do is to try and target what we would call hard to treat properties. So they would be traditionally things like solid wall, challenging pre-1980 builds, I think, typically. And the other category that we're targeting is hard to reach. So those are typically people that we would find difficult to engage with to talk about retrofit and the benefits of it. That part of the program is pretty much complete in the sense that we are oversubscribed. So basically all of those areas that I've just mentioned are now, we've filled all of our places, and we're now on the process of providing those whole house retrofit plans. So that's that part of it. The bit that's more relevant to tonight is we're looking to develop the skills within the existing industry, as well as trying to develop a new industry. And that new industry would be retrofit assessment, or relatively new anyway, retrofit assessment and retrofit coordination. So we have a fund of money, and what we're trying to do is encourage people to get into that particular area. Rather than going on about it, I'd encourage you, if you are interested, is go onto the Zero Carbon website. The web address is at the end. And into the retrofit section where there's funded training, and it goes through all of the funded training that we've got available. I'll kind of stop it there because I could go on for, it could be a webinar in itself. So I'll hand over to Diane now. Diane Hubbard, a leading airtightness expert in the UK. We're kind of really grateful that Diane has agreed to do these webinars for us. This is the first of two. The second one is next week, and it's assuming more knowledge of airtightness, but there's some crossover in both of those. So see how you get on to this afternoon. If you're still interested, then by all means come along to next week's seminar, which will take it on that bit further. Hopefully, as we understand a bit more about where you are in terms of airtightness, that would be fantastic. So I'll hand over to Diane now. Thank you very much. Thank you, Diane.
Great. Thanks very much indeed, John. My plan with this is to spend probably about sort of 35, 40 minutes talking, and then, so we should have plenty of time for questions. It's probably easier to pick up the questions at the end. If you really have something burning, I mean, I've got an odd slide where I'm going to ask you to think and maybe respond, but with questions, if you can actually put those into the chat or questions for John, he'll pick those up and we'll cover those at the end, and there'll be an opportunity to talk things through, with it being a relatively small group. So, right, so if I explain my background, so I'm really, my research area, my academic research area is pre-1900 houses, and particularly in relationship to ventilation and moisture in older buildings. I'm an engineer. I've passive house consultant, so I have I try and take an engineering approach to buildings, is what I do. And over quite a period of time, I realised that actually airtightness is key to so many things in buildings. It has such an impact on the performance of buildings that it really isn't treated with the level of priority generally that that it should be. And often that relationship that it has, it's thought of something in its own right, whereas actually it has such an impact on the performance of the building as a whole, both in terms of thermally and ventilation. So that's really it. That's where I've come to from doing all of this work over a dozen years or so. So I do stuff in relation to ventilation, for example, as well as airtightness, because it's all interlinked. Okay, so what are we actually talking about when we talk about airtightness? Well, what we have something called infiltration, and infiltration is uncontrolled ventilation. So it's not opening a window, it's not use of trickle vents. It's the stuff that we really are not controlling in any way. So when the wind blows, it blows into the building, or it on the leeward side, the air is leaving the building. And this diagram is quite old, but actually it's really helpful in terms of thinking about where those leakage paths are. Quite a lot are obvious, thinking about, around waste pipes and around doors, draft stripping and things can remedy that. But we're talking about less obvious things. What happens where you've got an internal soil pipe and that sort of thing. But the key thing is that infiltration, we've got to try and quantify it. And that's really what the airtightness is. It's putting a number on infiltration. So we have to be clear when we're talking about infiltration that is different from deliberate ventilation, things like extract fans and everything else. And that is separated under the building regs, but there is a clear dividing line between the two. So often, people often say, to start off with, they say, well, yeah, but, we need ventilation in the building. But the thing about infiltration is, it's coming from under the floorboards. It's coming through your loft insulation. Is it really the sort of ventilation that you want in your home? So being clear that infiltration is not deliberate ventilation. It's something that is unwanted. We don't need it, and it's absolutely undesirable in the building. The other thing that comes up in conversations quite a bit with people, they say, the building needs to breathe, right? Particularly when we're talking about old buildings, whether that's brick or stone buildings. Oh, no, we need that infiltration because the building has to breathe. Now, breathability is a really unhelpful word for people to use. People use it quite a lot when we're talking about pre-1900 homes. But what does it actually mean? And there is general confusion, I think, in the general public about, they think breathability is airtightness because it's got the word breathe in it. They assume it's about infiltration in the building. When breathability is used by professionals, what they actually mean is they mean vapor permeability. They mean the ability of water vapor to move within the building fabric. So we have to be a bit clearer about the terms that we're using sometimes, and I avoid ever using the word breathability because the public generally think of it, they relate it to airtightness, and actually that is nothing to do with airtightness or infiltration. It's all about moisture. So try and avoid using that word breathability. Differentiate between what's infiltration, that uncontrolled ventilation, and what is about moisture movement. Try and be more specific about the terms that you think in and that you use. Okay, so thinking about airtightness, it's a quantification of infiltration. We need to put a number on it. You know, there's an adage, isn't there, that, you know, if you don't put a number on it, you can't control it. I'm sure it's used by accountants. You've got to quantify it in order to set a goal and to know whether you're achieving it. And that's what airtightness is about. So in the picture in front of you, what we've got is a blower door. It happens to be in a listed Georgian house in this particular instance. But the blower door is the equipment that's used is the same equipment that is used for testing new build houses. It's just used in a slightly different way. So the blower door basically creates a pressure difference between inside and outside the building. And you can either increase the pressure inside the building or decrease the pressure inside the building compared to outside. Now, most of my time, a lot of the tests that I do are not to certify the building, they are to basically work out what is happening in the building. I call it a diagnostic airtightness test. And what I do with that is I depressurize the building compared to outside. And what that means is because the pressure is lower in the building, it means the air is drawn through all those cracks and crevices and holes. So those images that we can see on the right-hand side are thermal images of a building that's been depressurized. The top one shows a floor-wall junction, and we've got air coming in around the bottom. Where the plaster stops, we've got air coming in at the junction there where it just above the floor. And we've got cold air shooting up the wall and cold air being dragged across the floor. And that's what those cold fingers are. So the building is heated inside, it's cooler outside, and we're pulling the air into the building because the fan has depressurized the building. The bottom image there is of a conventional loft hatch, you know, a board sitting in a frame. And the board is held in place just with gravity. And when the building is depressurized, the cold air from the loft is being drawn around the perimeter of the wooden board, and they're cold fingers that you can see around those sides that's cooling the edge of the frame. And so you can see the extent of the cold air that's actually coming in. So in terms of what we're actually, sorry, I thought the next slide gave some numbers. What we're actually doing there is we create the pressure difference that we create is about 50 pascals. Now that won't mean anything to anybody, but it's the equivalent of a wind speed that's just over 20 miles an hour. So it's not a crazy wind speed. You know, it depends on the location. If you're on the top of the moors, then that will be quite a common occurrence. If you're in the middle of a city, it's less common. But it's not a crazy pressure we're talking about. And people are often staggered when I depressurize the building to 50 pascal that they can feel so much coming in. But it does represent conditions that it would be on a cool winter's night. The thing that is different is when the wind blows, on the windward side of the building, you know, under normal conditions, this would be, on the windward side of the building, it would be driving air through those cracks and around the windows. But on the leeward side, the air would be leaving. So it would be less obvious on the leeward side of the building where the leakage is to the person that occupies the building. But what the fan does, it's clearly the same pressure throughout the building. So that enables us to compare all characteristics of the building under these conditions. So we can see if the bay window on the front is leakier than the sash window on the back of the house, which is normally on the leeward side. And the client perception might be, oh, it's always that bay window that's the problem. But they're not aware of the sash window on the back because the air is leaving normally that way. But if the air wasn't leaving that way, it would be less driven in through the front window. So it's important that we look at the building as a whole. So this is a really useful test because it enables us to quantify where the air tightness of the building is on a scale. and it also enables us to fault find within the building. When you've got a new build house and you're doing this test, it's not heated usually because of the requirements of that test if it's one for certification. So we're looking at it under different conditions when I look at it with a thermal imaging camera and the building is heated. But it does enable us to understand what's actually happening in the building. So I'm going to come on to numbers and things in a couple of slides' time. But okay, so why is airtightness actually important to us? So the first thing is, and the most obvious thing is that, sorry, a cup of tea has appeared in front of me, is that infiltration increases the energy use. Yeah. So we of course need a certain level of ventilation in our buildings to make sure we've got good indoor air quality, right? And that's a whole day's presentation in itself about ventilation needs and things, but it falls outside the scope of this particular presentation. So there are ventilation requirements, but generally, if we've got a really leaky house, the energy use of that building will be higher. And when you're looking at buildings that are being retrofit, if the airtightness isn't addressed, it really significantly adversely affects the energy use of the building. I've looked at case studies where improving the airtightness sort of to, halving the air ingress. It's halved the energy use of the building. It's not unusual. It's down to the other characteristics of the building, but we're talking about this being very significant. Okay, air is relatively easy to heat, and it depends on what you're doing to the building, but infiltration definitely can significantly increase the energy use. So another issue with infiltration is thermal bypass. Now, what thermal bypass is you put some insulation into the building, right? And if it's not very well fitted, say if it's, say, we'll think of loft insulation at joist level, and say you choose to use some rigid insulation there rather than, say, an insulation batt. Now, one of the problems is that wood is going to have a slight wiggle on it. And however good and however straight the line of cut of the insulation is, there is likely to be some sort of air gap. It may come and go, but there's going to be some sort of air gap. And maybe there was a little bit of debris on the plasterboard of the ceiling that you're putting it down on, so it doesn't sit absolutely snugly firm on the bottom. The thing about all that is there's an opportunity for an air route for air to circulate around the insulation, and that will reduce the effectiveness of the insulation that's being put in place. And that particular issue, the illustration I've just given there, can be repeated through the walls, depending on the construction. And this is, we're not only talking about retrofit here, this is a significant problem with new build as well. So there are different sorts of thermal bypass, but basically what it is air moving either within the insulation or through the insulation that impacts the performance of the insulation. So the U values that are theoretically there may not be achieved and could be significantly impacted. So that's why another reason why airtightness is important. Moisture ingress into the building fabric. So we'll take an example of, say, a bathroom where there's around the services, you've got some air routes there. You've got warm, moist conditions in the bathroom, and the air can find routes along those air routes, and then it gets cool, and the moisture condenses. So you've got a mold risk then, and you've also got an increased risk with, say, any timber that's in that area, shortening the life of those works that have been done. Now, say if that's a timber frame new build, that can be pretty significant and impact the life of the building. It might be, it's some internal wall insulation, and there's a mold risk then occurring behind the insulation that's present. But it is a risk. If there aren't routes for the air, then the moisture cannot get into that building fabric. The other thing that is important is ventilation system performance. It has an impact on. So say if we've got mechanical ventilation heat recovery in a deep retrofit, there are planned air routes in that building for the air. But again, taking an example of a bathroom that's got maybe some leaks relating to where the services come in and out, then rather than drawing the air from the bedroom, it's perhaps more likely to draw air from through those service points, and then you're not getting either the ventilation in some spaces that you really should have, and you're potentially not getting the heat recovery that you should have. So airtightness isn't just about comfort and drafts. There are so many more implications for it. Okay, so what we're going to talk about now is a little bit on quantification and what does it all mean. So infiltration is putting a number on airtightness. So we've got the blower door test. Now there's a standard protocol that's worked to for testing new build houses. And when I test an existing building, I work to the same protocol as a new build house. And what that enables me to do is I can compare results with those new build houses and with all of the other properties that I test. There are clearly things in older buildings which do have a significant impact on the airflow in the building. For example, open fireplaces. You might have things like Argas or Rayburns, oil-fired, where they're drawing air from within the building. There could be a whole range of things, but open fireplaces and chimneys are a good example. And when you're trying to understand the building, what you're trying to do with infiltration is look at the building fabric, not necessarily the deliberate holes that you're making in the building fabric. What you can do, what the building designer would do, the person who's specifying the retrofit, would add those things back in afterwards. What we're trying to get to with the test is what is the fabric itself actually like? And the thing that I found when I did my academic research my initial academic research quite a long while ago, was actually generally the fabric is better than people generally expect. It's the other things that we do to the building that impacts it. So the approach that I take, and I would hope others take, is you work to a standard protocol, or the person that's carrying out the test works to a standard protocol that will enable you and the other people that you talk to be sure that the figure is calculated on the same basis as all of these other tests that are done. Now, people refer to, there's sort of two units that people refer to. One is air permeability and the other is air changes per hour. With air permeability, that is the measure that's generally used in the UK. So if you talk to anybody about what's the air tightness of a new build around the corner, the thing that they will be telling you is air permeability, or it's likely to be air permeability. But the easiest way to check that is with the units. Now, I know the units on screen look a little bit complicated, but if I just break it down, then hopefully you should be able to follow it. Okay. Ooh, sorry about that. The airflow in meters cubed, airflow of the fan, which is in meters cubed per hour, that's the first bit of that calculation, divided by the surface area of the building. Okay, so that's the envelope, it's the thermal envelope of the building. So it's the bottom floor, up the walls, all the way around all of the walls, and it's the top of the top floor ceiling. So you ignore any intermediate floors. There's a bit more to it than that, but broadly that's what we're talking about. Now this compares to air changes per hour, which relates to the building volume. So it's the airflow of the fan divided by the volume of the building. So how many times an hour the air is changing in that building. And both of those are done with the fan creating a difference of 50 pascals. So the air permeability is meters cube per hour from the fan at 50 pascal divided by the surface area of the building. Even if it's a mid-terraced house, you look at the party walls, it's all of the dwelling envelope is taken into account. So when you're talking to somebody about airtightness, you need to be clear which unit they're talking about. And the easiest way of verifying that is to ask them what the units are that they're referring to. And that will tell you whether they're talking about air permeability or air change rate. Okay, so you say, well, do I need to know the difference between the two? And I would say yes, because it can have quite an impact. Now, the house on the right-hand side is quite cuboid, yeah? And actually, that's got a very similar volume number to the surface area number in terms of, you know, square meters or cubic meters. But if you've got an L-shaped bungalow, that's got a much bigger surface area for the same volume. So yes, it does make a difference between the two. So you do need to be clear which one you're actually talking about. So here are some benchmarks that will help you to sort of understand the scale a little bit better. Okay, so before we started, we were talking, Stephen was mentioning about ACB level 2. Which sits at an air permeability of 2 meters cube per hour per meter squared at 50 pascal. We're looking at passive house. You see the numbers there are air change rates. So they work on a different basis. In the UK, we're generally working to air permeability. So much more airtight than the limit that we actually have for new build dwellings in the UK, which is currently at 8. An air permeability of 8. But typically, if you do a new build house, people are having to currently achieve about a 5 in terms of air permeability, where it's a gas central heating system. So hopefully that table gives you an idea of the sort of numbers that we might be talking about. But you know, if you compare a passive house to something that's built by, you know, a typical new build house, and you're looking, it's a million miles away. You know, it's a factor of 10 more airtight, broadly speaking. So we've got potentially a very wide range. So you're probably wondering, well, where does that put some of the other buildings that we've got here? I'm just aware of time, and I've got a few sort of more slides to cover on this, but there's quite an assortment of buildings here in front of us. The two on the right-hand side are new builds. The top one I tested not as a new build house. I had to test it, unfortunately, as a property that was experiencing some problems. So I had to carry out an investigation on that building. But, you know, I could ask you, well, which do you think is actually the most airtight building out of these? The castle in the middle was built in, I think, 1503, just out of interest. And I've tested all of these buildings. The castle isn't the least airtight, right? To give you an idea, the castle came out at about 12 in terms of where it is in terms of air permeability. The most airtight building on here is the one in the bottom right-hand side. As you would hope, it's a new build house. But interestingly, it was only very slightly better than the property that's in the bottom left-hand corner, which was built in the 1890s. So don't assume that an old building is going to be really leaky in terms of air permeability. Okay, so what does actually make for good airtightness? So the first thing is, when we're looking at older buildings, plaster is really important. Okay, so most building materials that we're dealing with, whether that's brick or stone rubble construction, block work, they let the air through. And plaster has a very small particle size and basically stops the air. So as a first starting point, when you're trying to sort of get your head around this subject, and if you're looking at an existing building, the thing to bear in mind is the places that are likely to leak are places where there is no plaster, right? Because it offers an easy route. Now, that might be where the plaster stops behind the skirting board. It might be where, a socket has been chased in for, a plug socket. But plaster traditionally creates the airtightness layer. So for example, if you're taking up plaster off a building and replacing it, say, with dot and dab plasterboard, but you've stripped the old plaster off, then actually that in itself is likely to have an adverse impact on the air tightness of the building. So what it sort of starts to come around to is you need to understand what you've got already and then think about how you're going to make it more airtight. Okay, so what I've got here is a few images to sort of illustrate what I've just been showing you. Again, I'm just aware of time, so I'm going to drop to the lower image there. And this was taken actually in the new build house that I had to test, was having some issues with energy use, and I was brought in to try and work out what the problem was. And the thermal image on the bottom left-hand side, the daylight image on the bottom right-hand side corresponds to that thermal image. And what we have here is it's dot and dab plasterboard that has not been edge sealed. And when the building is depressurized, it shows that air moves behind the plasterboard and is drawn down from the loft bypassing any insulation in the wall and cools the top of the ceiling, the top of the wall where it joins the ceiling. And so we can see these dark areas which are cooler. You can see that it's quite significantly cooler looking at the temperatures that we're seeing there. But that's an example of thermal bypass. Because it's plasterboard that has not been edge sealed, it's just been applied with dabs. Okay, so how are you going to achieve airtightness? Okay, so this is specifically with respect to retrofit, and it applies to any age of retrofit, but I mean, we're particularly looking at older buildings. Okay, so the first thing is know where you are starting from. You've got to decide what your target is, develop a strategy. So know where you're starting from. There's quite a range of building air tightnesses. Don't assume an old building is really leaky. Some of them are, but some of them aren't. It depends on what you're trying to achieve as well as to how much work you have to do to get there. But if you don't know what you're starting from, then the designer of the work, whether that be yourself or an architect, does not know what measures are appropriate and how easy that final target is to achieve. So in terms of decide what your target is, that clearly depends on the budget that somebody has and where their priorities are, what they're trying to achieve from the project. And if you don't know, you need to know where you're starting from and what your objectives are, and then the strategy can be designed. And don't underestimate how important that is. We're very good in the UK. We're really good at winging it, basically. And airtightness needs a certain level of understanding and design in order for it to be effective. You have to have a strategy which thinks through every junction, what is happening at that point, to make sure there's continuity of the airtightness layer. Every time the airtightness layer is breached, okay, how do we do it? What is the airtightness layer? In this instance, is it plaster? Are we using something else to create the airtightness layer? It really depends on what your objectives are. The aim of this presentation is to give you a flavour for what needs to be considered rather than go into detail over materials. But you have to have a strategy. That might be in your head. It's much better if it's actually on paper. It's much better if it's properly designed. You've got to make sure that you have the ability to achieve the aim. Now, if you're trying to get from 20 to 10, that's a lot easier than if you're trying to get from 10 to, say, 2 in terms of air permeability. You need to be able to control what's happening with the other trades that are involved on site. You know, do people understand what the airtightness requirements are? Is everybody doing what they need to in order to make sure that that airtightness is achieved? And some people you know, do require testing on completion of the airtightness layer. It's very, unfortunately, quite sadly, sometimes people just get a test done right at the very end because they're thinking of, oh, I want to get certified or something else, and the kitchen's in and the bathroom is in. And you can't get to anything at that point. If you test at that point, all you're doing is putting a number on what the airtightness of the building is. But if you test when the airtightness layer is complete, so that's broadly first fix stage, you know, when you've got the windows in, you've got all of the airtightness materials, the taping and the plaster and everything else done. If you test at that point, everything is accessible and it's really straightforward to rectify any issues that are found. And there will be issues, right? Because we're all human, and however good a job we all try and do, we always miss something. So it's a really cost-effective way of making sure that the airtightness is achieved by testing at the completion of the airtightness layer, particularly if contractually the client is expecting a particular airtightness. The stress that it puts on the contractor to not test at that point can be quite severe. And it makes everybody a lot more comfortable if you do a test at that point and you can be certain then that you've achieved what the client is after, or it's an opportunity to get those measures, get the extra works done that are needed. Once everything is hidden behind all of the you know, the sanitary fittings and the kitchen units, you just can't get to it. Okay, so know where we're starting from. This is an example of me doing a diagnostic test in a building and looking at it with thermography. So those images that I've shown you already illustrate what happens in a test. So that's before the design is done. You know what we're starting from. And this is a particular benefit where it's a very limited budget. So you may not be able to throw everything at it. If you're completely gutting the building and say going for passive house, for Enofit, say, then to a certain extent, this isn't needed. But if you've got sort of a smaller budget and you're trying to decide what works to actually do, then this is really helpful to do at this point. Okay, so this is an example of a building, a 1990s building, which had some 2000, an extension done in 2000. And this thermal image is actually in that, the left-hand side of the rear extension. So the one that's got a gable end towards us is in that image on the top left. And that was built around 2000-ish. And this is the ceiling in that room. And It just illustrates that under a diagnostic test, we can see that there are whole areas in the ceiling which are missing insulation. And there is an air tightness problem about this. That's a piece of timber going across the screen. There is quite an air tightness problem there. That's not saying that that's wrong when it was constructed, but if you're looking at what you do to that building, images like that really guide what's required. This is another example. This is a bath. It might look like water that's flowing down the side of the bath, but actually that's cold air coming in around where the waste pipe comes through the wall. Very dramatic, but you wouldn't necessarily be aware of it being there if it was on the leeward side of the building. Okay, deciding what your target is, that is down to the client budget. Developing the strategy, you have to design it in. It's not all about fancy materials. It's down to how you do it, and the standard to which it's done. But it has to be designed in, because magically air tightness won't just happen. You have to have a designed air tightness layer. And developing the strategy on that, basically, it is a case of sitting down with the drawings and a red pen on both the plans and the sections, and literally drawing a red line around the building to say where the air tightness layer is and what goes through it, where are the junctions, and how is every single one of those treated from an air tightness point of view, whatever the materials that are being used for that particular building. So workmanship, how do you do it? Set clear goals and a clear specification. Have somebody that champions what's happening. Make sure everybody is clear about it. It's down to everybody takes part in this. Everybody has a responsibility for making sure that building performs at the end. You know, you need to lead it. If you're passionate about it, then your team will be passionate about it. It's really important to avoid blame, though. You need to make sure that people are prepared to say, look, I accidentally cut through that membrane when I was putting that pipe next to it. Because if people understand why the air tightness is needed, then they need to be able to feel that they can raise issues that are occurring, because the last thing you want is to not be aware of a problem and then it comes out on the air tightness test, particularly if you're not going for one at the intermediate stage, at the first stage, at completion of the air tightness layer. Okay, so yeah, have you achieved your target? You know, I've got lots and lots of images of buildings where things, you know, we're trying to do our best, but things do get missed. A line of tape gets accidentally missed. You can sort it out if you do an air tightness test. At that stage, the building would need to be heated. In this case, I'm using thermography, so it needs some heat in there. But you can be certain that if you do that test at that stage, then the building is well on the way to getting the standard that's required. Okay, so they're the key things that you really need to bear in mind when you're doing it. I'm aware I've overrun a bit on those, so I would suggest I call an end to it there and I take questions. I'm aware that we started a little bit late. So are there any questions?
Not as yet. Is anyone
John?
Questions? I'm looking at the chat. There's nothing coming up at the moment.
Okay. Anyone want to say anything? Do you want to come off silent, guys, and we can have a conversation about it? Anything that you would like to raise?
I found it very interesting. I've done it from both a personal point of view, because I've got a very leaky house, and obviously from a work point of view. So just found it fascinating. Yeah, thank you.
Okay. Are there any specific questions on that? I mean, lots of people, in terms of this test, I actually did one yesterday for a guy who works for a construction company, who I think he does stuff on the costing side of things. And he'd seen an airtightness test on a new build, and he was trying to decide on his rather nice house whether he put a heat pump in or should put a heat pump in. But his house is from the 1970s, and it has an air heating system, not a conventional wet heating system. So the air tightness is quite important from that point of view. So his heating's even, being driven by air movement within the building. And it was interesting that even though he works in the industry, he really hadn't made the link between, hadn't sort of put it all together really. So air tightness has such an impact on everything else, and the performance of the insulation is so important. Our new builds consume way more energy than they should, and one of the factors will be down to the insulation not performing as well as it should because of poor air tightness.
Yeah, my house is 2012, and from an EPC point of view, it reads well, but to actually live in it, it's terrible. I think the front door's got about just over 3/4 of an inch gap, and then 2 of the windows have been really poorly fitted, so the draft that comes through in the winter is terrible. But it's one of them things you don't really start to look into it until you start looking at this kind of thing,
Yeah. I mean, there'll be some relatively straightforward measures that you could apply to your own home that would improve the air tightness and improve your comfort. Clearly, it would be, 2012 house. It may have been tested. The air tightness testing industry was a bit dodgy still at that point. It wasn't. It's only very recently every new build house has had to be tested. So yes, it could be not great, but there's an assumption that older buildings are going to be worse, but they aren't necessarily. I've tested a lot of pre-1900 buildings. I've done timber frame houses, castles, you name it, I've done it, and you would be surprised how many of them are actually comparable to our new build limit that we have. It's quite shocking, really, in terms of air tightness. Yeah.
I think into some respects, our capacity as builders and constructions gone on a downward spiral over a period of years, hasn't it?
Well, no, I mean we have pressures, and most people say, how cheap can you do it? Yeah. I think the market. People might say I'm fortunate in the market that I work within, but the market I work in is definitely growing, because what people are doing is they're looking at what's the combination of how much I'm spending on this work and my fuel bills in the future. And the reason why people talk about numbers on air tightness is because they know their fuel bills are going to be lower in the future. And particularly, you're buying or remodeling the home that's going to be your retirement home. You've got a fixed income, or you've got a certain, you know what your income's going to be. You want your fuel bills to be low, and you want your home to be easier to heat. And that's particularly the market. They've got the money to spend it. A number of them have got money to spend on it. And that able to pay market is quite focused on what are my future bills going to be, and certainty of those fuel bills. So, that sort of archetype of person is definitely driving this particular market. And, who wouldn't, if you can set a target and the building performs better, then that seems very sensible to me. But I'm bound to say that to a certain extent, because that's why I'm doing this, because I'm very passionate about it, and I don't think it's appreciated as much as it should be in terms of air tightness. Any other questions? Anybody else there?
I was going to add, I think it's coming to all of us in terms of building efficiency, in terms of air tightness and lowering of bills. I mean, it was only this week I read that it was a builder, they're offering 10-year no energy bills, in Norfolk, I believe, or Suffolk. I think it was Suffolk or Norfolk, one of the two. And that's been announced. So it's obviously it's the way things are going, is more and more efficient buildings, and we've got a building stock that we need to kind of retrofit. And as you've pointed out, Diane, and the importance of airtightness is significant in terms of energy loss. So if you're looking to retrofit a property, then going in at the start, knowing what you're dealing with in terms of how leaky or permeable or whatever that property is, just makes complete sense. So I think the conversation that Diane, well, I had a meeting with Diane yesterday in terms of where this might happen, and looking at the retrofit assessment, which is very much the start of a retrofit journey, is where ideally we'd look to put air testing as a start, so you know exactly what you're dealing with, and then you form a strategy from there, and you're getting more bang for your buck rather than taking guesses about, oh well, we might put some EWI on there, or we might put some more loft insulation in. Is looking at where are you leaking, where you're transferring heat outward or bringing cold air in. So yeah, it just makes complete sense.
Yeah.
Anyone else? No, there's nothing coming up. So
Okay.
So they're all convinced and ready to go.
Good. Okay. Well, maybe I'll see. It would be great to see you all next time at the next presentation, where I'll go into some more. I'm just trying to give an overview in this presentation, and there's clearly a lot more detail involved in it. But hopefully, I've given you enough of an outline to give you a quick taster of what airtightness is all about.
That's great. Thank you very much, Diane. Really appreciated. Just to let everybody know, we have recorded this, and we'll make it available on the website, as we will deal with next week. So if anyone wants to revisit it, or colleagues, etc., friends that feel it will be of use, please forward that on. Obviously, also forward on the link for next week's webinar, so you can find all of that at our website, the zerocarbonharrogate.org.uk, and then just go to the retrofit section and training, and it's all listed there. And I think that probably closes it. So, well, thank you again, Diane, and thank you everyone for attending. I hope you found it useful. We'd certainly be interested in your feedback of what, whether it was interesting, whether there's something else that you wanted to be covered. And yeah, if you let us know, that would be great. Thank you very much. We'll call it there.
Great. Okay. I've got to hop off sharpish,
Okay.
but we'll have a follow-up conversation if that's all right.
Yes, that'd be great,
Just to recap on things. If I'm not needed at this moment, I will give you a quick I'll send you a message. Okay, but I think I have to go into this next thing virtually straight away. I think they're setting up, so I better go. Okay. Was that okay?
That was brilliant. Thank you very much.
Okay. Right. Take care. Speak to you soon.
Bye-bye.
Bye.